Okay, we are beginning our call tonight for the Bucky call for the weekend of March 7th and 8th. I'm on a new computer and I still got a few bugs to work out. And so pardon me for my slow start tonight, and we'll get rolling. Also, I'm going to be leaving um, to go attend. My son has a concert, and so I'm going to be leaving in about 20 minutes. And so I'll start the call with you guys. And I would be glad to Fred will be conducting the meeting tonight, and I would be glad to be the first guy to share, or whoever you point, Fred. But I will be leaving before I go. Let me think, is there anything else?
All right, thank
No,
you.
I think I'm good, and I'm going to hand it off to you, Fred.
So thank you. So I handle that for all of us tonight. So Stephen, you first tonight. How are you feeling today, and what would you like to take away
All
in
right,
those
well,
20 in the 20 minutes you have?
in 20 minutes. I would, how am I feeling? Well, I feel a little bit upset when I think I have my computer running from last week and it's not quite running the same way. I'm using two systems, however, and so I'm creating my own problems. And so I'm going to deep breathe and join the call. I feel like that what we're doing with Amy's book here, Amy Edmondson's book, learning about these bow ties and folding systems here with these vector equilibrium are very exciting to me. And these are things which I think I need to go back and review again sometime. And I'm looking forward to getting further knowledge as we pursue the call. Lee, how are you feeling tonight? And what do you anticipate getting out of tonight's?
You muted Lee.
I've got to help her find her screen. And so, Joe, how are you feeling? And when Lee's microphone starts off, Fred, she's ready to share anytime after that. Joe, how are you feeling, and what do you anticipate for this evening?
I'm feeling actually pretty good, actually. Again, as I stated, really emotional, period. Probably the hardest emotional thing that I'm going through. And yeah, so I'm on edge a little bit. But I'm feeling good because I made a lot of progress. So that once that transition is finally over, and everything's done, that it'll be different. So my expectation for the call is to actually, as we get back into the book, I'm looking at things through a little bit of a different lens now, through a different framework. Using the Philosopher's Stone, the ones that I shared with you. So, and I think that that's really going to be beneficial for me on a way of kind of backtracking ideas into, Bucky's ideas, and I'm really excited. In one regard, I think I've really come across something around AI that it's going to be good, that we'll be able to maybe share at some point a little bit more about how AI is a mirror of our behavior, and deception is part of that. And so how that is actually something that needs to be thought out. So Manu, or Lee, forgive me. How are you feeling? What would you like to take away from today?
Finally, I got online. I feel good. It's an exciting day. I have basically done nothing. I should have been doing a lot, but I'm excited about finding out more about bow ties and just everything. So, Manu, how do you feel? And what would you like to take from this meeting tonight?
I feel good. Good morning to everybody. Yeah. I feel a little bit like a wiggler. because the
folks
cosmos, like a wiggler, wiggling, somebody wiggling. Because the cosmos being harmonic, being playing a symphony. For event to happen, I need to wiggle. If I wiggle, I create disturbances and I create visible pattern that I can see other than the IVM, and which makes sense to me. So that's the way I feel. What I expect is that we progress well on this book. We're spending a lot of time on it, but I see that it's coming back to the beautiful formula of beautiful identity, Euler identity, and yeah, I look forward to a good ride. Oh, so who's left? Fred? Fred, how do you feel? What do you expect to take away?
Thank you, Manu. I'm feeling like crap because France lost, but we lost against a wonderful Scottish team. So that was a good match. They played better than us. They just gave us a wonderful game. And I feel good because England lost. I don't know against who, but it doesn't matter. When England loses, it's always a good day. So I hope to take away a little bit of a cheer up from this call. That's what I hope to get away. So, if there are other questions or remarks from last time that you would like to address before we get on to the reading? No. So I will share my screen. Who would like to read?
I can attempt.
Joe, will you read?
Yeah, sure.
Okay, thank you.
So foldable systems. Just
Yes.
as we needed at least 4 vertices to make a system, 4 is also the minimum number of great circles that may be folded into local bow ties and fastened corner to corner to make the whole sphere. An interesting characteristic of this minimum model is that the sum of the areas of its 4 separate circles, which fold up to create the model, is equal to the surface area of the sphere they define, or 4 pi r. Structured out of that number of bow ties. But in some cases, the pattern can be simulated using more than prescribed number of paper discs and doubling the polyhedral edges. You cannot make a spherical octahedron or a spherical tetrahedron by itself, 109 degrees to 28 degrees. I can't, that's hard to see for me. Of angle cannot be broken up into 360 degrees, spherical increments. I'm assuming that's synergetics it's referring to there. A spherical tetrahedron can only be created out of foldable paper circles by constructing the 6 great circle spherical cube, which produces 2 intersecting tetrahedra. See figure 14-6. 6 great circles will submit to a bow tie construction similar to the 4 great circle model described below.
Any questions, any remarks at this stage? I'd like to say that the surface of a sphere 4 r square is very interesting because it's a very simple formula, and it's 4 times the surface of a disk of the same diameter, same radius. It's a remarkable result.
Fred,
Yes?
can you make that screen a little larger so I can see it properly? Because a lot of it I cannot see.
Yeah, it is a little small, but
It's too small? Okay, hold on.
yeah, I mean it's pretty small.
Okay.
My eyes are bad anyway, but there we go.
Is it better?
Well, you're kind of cutting off the edges there.
Oh, it's
Yeah.
cut on the edge. Okay. My windows are overlapping, so I have to go back and forth.
Uh-oh.
I think that's going to be the biggest you can get.
Is that better?
Sure.
Should be good, huh? Okay. So 14.16, 6 bow ties create the 6 grid circles of the cube or octahedron.
That's interesting.
Can
You know,
everybody see? Can everybody see the 6th grade circle? Clean.
yeah, I can. And you know, it's really interesting to see this. As I mentioned, I'm looking at everything through the idea of a philosopher's stone. But you can also see how the stars, like whether it be with the Star of David or a Seal of Solomon, you could see that clearly within the cube, which is, you know, Lee, I'm sorry, you had your hand up.
Oh, I'm sorry, I didn't take it down.
No,
You made it bigger.
You should speak first.
It was for getting it bigger, and he did.
Oh,
Thank you.
okay. So, yeah, no, and what happens is by looking at it through that lens, it brings context to what these, you know, how these symbols interact, because you're kind of, it's just helping with viewing it and starting to understand the B, the A, B, and you know, how the 6 great circles of the cube octahedron actually, how bow ties are related to them.
Okay. Can I share a little bit of something?
Sure, please go ahead.
You remember this, the Star of David?
Let me unshare something. Share. How do I unshare here? Here. There we go. Stop sharing.
You remember this Star of David? Huh? It's 2 tetrahedra intersecting. That's the Star of David. It's also the representation of original tetrahedron that is divided twice into the stellar part and the implied octahedron in the middle. Do we see that?
Yes.
Okay. Now, you remember the 3 great circles of these, right? You see the green, the yellow, and you see the red? The red here.
Yes. Yeah.
You see the green? Yeah.
Kind of, yes. I mean, I can kind
It's
of,
a little bit faded now.
yeah,
Because
yeah.
it's been out there. And then you see the green, and then you see the blue. Now, this
Yeah.
was the green. This is green. This is supposed to be green, like this. And then you see the blue one here. So we agreed that we've delineated 3 great circles already. This one, that is the red. This is the blue here, where my finger is going through. And this is the gold or orange, whatever here. That is 3. Now, if you take the tetrahedra that are stellar, and you take every 2 opposite, you have another 3. Look at this one. This is 1. This is 2. And that one is 3. Those are the 6 great circles. And it's an interesting exercise to do the Star of David, like this, and then to number each of the 50. each of the faces, you are going to have 24 faces. This is number 24 here.
Yeah. Wow, that's
Okay.
the best description I've seen. Yeah, it's
Yeah.
by going through those
But-
circles.
Yeah, but we did this right at the beginning of this book. But it is there. That's what she talked about.
That's fantastic.
Yeah. I encourage everybody to do that. You do the way you do this is that you do an octahedron. Everything is equilateral. You do an octahedron like Steve usually share, and then you do 1, 2, the 8 tetrahedra, and then you put them on the faces of the octahedron. Then you have a stellar. You have two intersecting tetrahedra, and you have a Star of David, and then you can see these things.
Mm.
Okay.
Yeah, no, that's perfect. That's a
Just tetrahedra. Yeah.
but it's amazing how you can have that. I can, it just changes your orientation when you have context to it.
Yeah. And what she showed here, if you look at figure 1415b or even 1416, it's just that she took the envelope of the apexes of each of these. You see, you put a dash here, and dash there, and then she's calculated the surface of the sphere, this big sphere that is around you. In other words, yeah. This is a very good description. We can also do it with the magnets. With a magnet, I think Steve has it. To have a... Okay. You can see it on the cube octahedron here. Look at this. Let me show you. Now, it's delicate. Oh, the other one, everything in space is trying to connect. Let me pull out this one. It was interesting that the mite just connected to this when I was carrying that stuff. But look at this. You see the yellow part of this?
Yeah.
And then
You
you
could
see
draw the circles.
yes. And
Go
then you
right
see the
around.
octahedron. You see the octahedron in the middle.
That's right.
Yes, that's it.
Wow.
That's that part. And everything that is at the top here to contribute to closing is a mite. The mite will do things. But that is another presentation of it.
That's the bow tie.
Yeah, that's wait, you can see the Star of David in yellow.
Yes, absolutely.
Yeah.
It's clear as day too.
Yeah. Okay.
And you can also see the square in there too. Yeah.
You can see the square because this was remember the cube octahedron.
Yeah.
This was the cube octahedron. Okay.
Yeah, that's awesome because you could. I mean, everything I'm putting through a different lens. That's all.
Yeah.
And
just take the magnet. I hope you have. For everybody who has this set
I
of
just
magnet,
do. Yeah.
yes, and build it. I hope that you can, just put in the colors.
And I think the helpful part is having a boundary. Like now I'm looking at it. When I'm looking at it, I see when you see the Star of David or the Seal of Solomon, that you put a boundary around it, like you can see it much more clearly about how it's constructed.
Yeah.
And the bow tie itself.
Yeah. And remember that all we studying here is that we taking the closely packed sphere and we're looking at how to fill the gap between the spheres, the convex part.
Yes, yeah.
You remember that's what we are building.
Concave, yeah. Concave,
We
yeah.
put in closely packed sphere. We know that closely packed sphere don't fill the whole space. There are gaps. There are stellar gaps that come between the spheres. And we are looking to fill the sphere. If you want to measure the whole volume of the sphere, we need to find things, units, that allow us to get into it, either from the macro point of view or from the micro point of view. From the macro point of view, we study the cube octahedron. From a micro point of view, we look at it from the mite. Notice that two mites presented three-quarter, like this actually fill those gaps. So they build a hole from filling the gaps. And at the same time, preserving the octahedron in the middle, if you just combine mites. So you are filling from the minimum, from the micro. Or you can look at it from the macro point of view. This is a macro view. That is, you have the most expanded form of a finite universe. And then you are counting, you are dividing in such a way that you account for everything. That is the little exercise. We've always been, with all of this construction, doing arithmetics. It's always about measuring. So like Kelly would say, leading calibrators that are words, that is the syllabus that we use to describe.
Yes.
And lagging calibrator, that's our numbers. We have to calculate, we have to
words
divide.
lead,
Yes.
words lead,
And then
numbers
the
lag.
whole has to be in such a way that what we say means what we measure.
Yes.
What we say, what gets in our system of thought should reflect what we get out. That is measured. Okay, I'm through.
That's
Thank
awesome.
you, Manu. Richard, welcome. And how are you feeling today? And what would you like to take away?
I'm feeling pretty good as we are into springtime weather again and anticipating snow in a day or two. So it keeps coming and going. Yeah, I'm back into my own copy of the book, so I'm looking forward as our exploration of chapter 15 and I had an interesting experience with the star tetrahedron not so long ago, as I've been experimenting with these AI questions. And so I framed a question that actually created a response to sort of tetrahedron shapes responses. And so then I said something about how about a way to interweave these two tetrahedrons. And the answer that came back was put them in a star tetrahedron configuration, just like Manu was showing and describing and illustrating. So it was interesting that these geometric structures are available out of some of these large language sort of data sets, and it was nice to see them apply it to me in that interweaving kind of context. So yeah, there's, and you know, as Manu and all of us, I guess, in many ways talk about, we're interested in finding applied sort of illustrations of what can be done with some of these geometric understandings, and that certainly was one for me. Yes. So I'm sorry I was a bit late, and we had one of our daughters here, and we were out for a bit of a dinner, and now I'm free and available to carry on with the dialogue.
Thank you, Richard. We're on page, I think 249 now. I'm going to share my screen again, unless there's more comments.
I do. I just wanted to say today I was talking with a neighbor, and she was standing right there next to a food that was a hexagon, and she had triangles all around her because her granddaughter, a very young toddler, had all kinds of what we've been talking about. And this little girl, was playing with two diamonds, and they made a bow tie. And I said, there's math. You should be teaching her what they are, the names of those creations that are in your kitchen. And it was really fun. It was very nice to be able to explain to her what I've been learning. I'm done. Thank you.
Thank you.
Thank you.
Oh, nice. That's good
Nice.
size.
Yes.
Joe, you up to keep going?
Yes. So 842-04. Nor can we project the spherical octahedron by folding 3 great circles. The only way is by making 6 great circles with all the edges double. In this construction, 6 circles are folded in half, and then the resulting semicircles are each folded in the middle at a right angle. The 6 semicircle pancakes, rather than 3 open bow ties, are then simply pinned together to simulate the 3 great circles of the octahedron, figure 14-7. Interesting. That's an interesting way of presenting it as well. Boy, things become so much more clear when you have a frame.
Manu,
Yeah.
you have the floor.
Manu?
She's
Now you
talking
have
about
that.
is the exercise that we did a few weekends ago. Is this one? Is this model? This is the one here. The 1417 is exactly this one.
Mm-hmm.
The 3 great circle of the octahedron. 1, 2, 3.
Okay, is there more?
Yes, that's all.
Thank you.
Fuller
Okay, Joe.
attributes these discoveries to a basic cosmic sixness. There is a basic cosmic sixness of the 2 sets of tetrahedra in the vector equilibrium. There is a basic cosmic sixness. I do not like that, but also in an octahedron minimally great circle produced of 6 great circles. You can see only 3 because they are doubled up. And there are also 6 great circles occurring in the icosahedron. M, what is that? I can't see.
Am I?
Is that MI?
It
Is
looks
that what
like.
it?
That stands for something, doesn't it?
Yeah, I'm not familiar with it. What it means.
ML, maybe?
Should we look that up? I would assume. Hang on.
Am I? I don't know.
I don't see the two
Well,
lines on the bottom and top. So it might be L, ML, lowercase l.
yeah, I think we'll have to come back to that. That's bothering me though. These are foilable. The sixness corresponds to our six quanta, our six vectors that make one quantum, 842.05 842.06. Both six great circle patterns can be constructed out of foilable circles. The star tetrahedron version involves six bow ties with two right isosceles triangles on the surface, 60 degrees, 60 degrees, 90 degrees, created by central angles of 70 degrees, 32. A and 54 degrees, which is in 54 and 44, I'm sorry. B, as labeled in figure 14-16, the six bow ties are pinned together at the seams to create the 24 surface triangles of the spherical cube and star tetrahedron. And it works. The illusion of six continuous circles is maintained. The icosahedral six great circles fold into pentagonal bow ties. Fold lines divide each circle into 10 equal slices of pie, carving out the 36-degree angles. Each circle is then pinched together at one point to form a double pentagon figure eight. Literally like figure eight. Just like the triangle predecessors, each circle folds into a local circuit and is connected to other local circuits to create the illusion of continuous great circles, figure 14-18. And then you have the six pentagonal bow ties. Well, you can see it.
I'm going to go back to 16 to figure 14.16 to look at the angle A and B, 70.32 and 54.44 degrees. So we have A and B here, angles. I don't understand those angles. They look the same to me.
They look the same to you? When you're
They
looking at
actually do.
when you're looking at in the corner, obviously. They appear
Okay, I
the same
guess
to me. They appear the same to me as well, actually.
actually, I guess we have to build one ourselves, which I have not done yet, in order to get a better feel of it.
Look at it from this point of view.
Okay, go ahead.
We are collapsing things into a plane
Oh,
for an illusion. One is
Okay,
a
got
double
it.
time. You got it?
Got it.
Okay.
You project it.
Yes.
You project it. Okay, so you lose.
Yeah.
You
Yeah.
lose some of
It is the same thing that
And-
we're doing. The same exercise that we did with the boundary. It's
Yes,
similar. Okay.
yes. So you're losing the angular integrity. Okay, thank you for
Yes.
that, Manu. I appreciate it.
that's helpful for me, actually, for something else.
Now where were we here?
Oh, we stopped at
And is it-
figure 14-8, six pentagonal bow ties create the six great circles of the icosahedron. Yeah. Fuller experiments with the foldability of considerably more intricate patterns larger numbers of great circles intersect frequently, and arc segments have correspondingly smaller central angles. The number of folds and the precision required for each of the tiny irregular angles make these higher frequency models extraordinarily difficult to build, and even more difficult to visualize without a model. Each of the 10 great circles of the icosahedron can fold into winding chains of six narrow tetrahedra, which then interlink to reproduce the 10 great circle pattern. Now that's something I need to revisit. Anyway, I need to go back and read that again. Fuller claims that the 15 great circle pattern outlining the 120 LCD units can be reconstructed with 15 four tetrahedron chains, 458.12. While a paper circle will fold into 4 consecutive LCD tetrahedra, it is not clear how they fit together to create the whole sphere. We note, however, that this pattern can be easily generated by using 30 paper circles and doubling the edges. Each circle folds into 4 adjacent LCD tetrahedra. To form one self-contained diamond, a face of the rhombic tricontrahedron. Triacontrahedron.
Triacontrahedron. Thank you.
Yeah, there's an A in there. Figure 14-9, 15 great circle model created by doubling the edges. For the purpose of this chapter, we want to understand the basics of how foldable great circles work. Further experimentation with construction paper is left to curious and ambitious readers. I'm sorry, ambiguous. We proceed to look at Fuller's interpretation of the significance of this behavior in terms of physical reality. Manu. You're on mute, Manu.
Manu, go ahead.
Okay. I was going to say that all of this proceeds from the very first principle. The principle is that in space, i.e., in cosmos, there's no void. Energy is everywhere. Energy flows. Energy always flows. And energy flows to the line of least resistance. So if we have that, if we take it as a principle, then energy does not jump. Everything happens for a reason. That is, there is a cause to everything. So you can chart a path that is continuous from one event to the other event. And I think that that is a basic principle that we should have in mind to understand the complexities of the foldability. It is infinitely foldable and unfoldable within a finite realm. Yes, I'm true.
Thank you.
I today had another friend come in to visit me in my apartment, and he was fascinated with crystals and rocks. I have lots and lots and lots of maybe too many rocks in my house. And I was showing him the different kinds of crystals. And there was one that shocked him. He says, isn't there supposed to be a triangle up at the top of this point? And I said, not necessarily. I'll show you a crystal. And it was a total, complete square. And I was fascinated at how all these different measurements that we're learning, we can still find a square somewhere. And maybe not right now, but we have in the past. And that is so neat that I could show him the crystals of all these different kinds of stones, including a flat one that were 2, 4, or 3 circles instead of crystals that had points, a tetrahedron. So it was quite nice. It was very interesting to see all that I am studying now with all of you, uh, and how nature has it everywhere. Thank you.
Thank you, Lee. I'm going to share again. Share. Yes.
Energy
Joe,
path.
okay, go ahead.
Here's
Thank
the
you.
basic premise. First, the concept of a sphere provides a model of the generalized system. On the surface of a sphere, the shortest route is a geodesic path. Secondly, universe breaks down into discrete systems, which consist exclusively of energy events and their relationships. And finally, energy is always in motion, perpetually transferred between finite local systems along most direct routes. And therefore, energy must be traveling through universe via great circle paths. Gas molecules. We consider a specific example. A vast number of molecules of gas interacting in each circles inside of a sphere will produce a number of great circle triangles. The velocity of their accomplishment of this structural system of total intertriangulation averaging will seem to be instantaneous to the human observer. I'm a little struggling.
Can we please read that again?
The whole section?
Starting at a vast number of molecules.
We consider a vast number of molecules of gas interacting in great circles inside of a sphere will produce a number of great circle triangles. The velocity of their accomplishment of this structural system of total intertriangulation averaging will seem to be instantaneous to the human observer.
Thank you. I have no idea what he's talking about.
I think that I don't either. I'm not going to pretend. But when he's talking about I mean, I feel like in a way he's talking about, I don't know, it would seem to be instantaneous to the observer is what I'm focusing on, because I almost feel like he's talking about lag, but I don't think that that's the case.
A vast number of molecules of gas interacting in great circles. Somebody knows what that means? Manu? You're muted.
You're mute.
Yes, I want to share two things. The icosahedron and the dodecahedron together, forming a whole. We see only what is stable, what form a pattern. What we see in this is these triangles here, and there are 20 of them that connect only vertex to vertex. That is the first figure. Keep this in mind. Look at this one now. I've been experimenting with something. Take the mite and put it here. You see the mite here? Or let me put it this way. Oh, difficult to hold. Okay. You see that?
Mhm.
You see how it constructs?
Uh-huh.
This is the hole that you see. And energy flow here. Energy is everywhere and flow. So
Yeah,
what
you
Fuller,
can see that. Yeah, it's odd, but you can see it.
The gases are flowing.
yeah, there's energy
Well,
everywhere
you can
here.
see it everywhere. I mean,
Yeah.
it doesn't look
But
as
on
strong.
this one, energy is flowing actually through lines of least resistance, which are the great circles here. You can see the great circles. We've already seen this 31 was how many great circles that we had here? Energy flows through the lines to form patterns that appear like to be gases. And it's the most expanded energy, like this is the concept of the most expanded state of universe. Let's call it universe or cosmos.
Hmm.
In the most expanded state of universe, that is, we are looking from inside the sphere. Everything look connected vertex to vertex to form
Interesting.
the sphere that is the orthogonal relationship of the icosahedron and the dodecahedron is dual. It is the two interact like in the Star of David.
Yeah.
It's the same configuration. It's the same assumption of duality at the largest and complementariness. Do you see that?
Yeah, I did.
This is the icosahedron, and the void are dodecahedra, a dodecahedron, and the two combine to form the sphere. And we know that the sphere is the most expanded whatever that we know. And that sphere is, we can see it in the form of the intersection of many lines of great circles is apparent that allow for energy flow, and that form the pattern that we see. The pattern that we see is that of the icosahedron. That's what we see, because we don't see the voids. We see the pattern formed by the stable. Every closure here is a triangle. Every closure is a triangle. So we see what we can call an expanded icosahedron or a gaseous bonding structure. That is vertex to vertex. But obviously we can squash this to what we want. We can do this, and this is intertransformation. That is, if we press, it will go to a certain way. And remember that if we squash this thing, if you see through this, every pentagon is actually facing the other side, another pentagon. What I mean is that if I go straight, vertical, like this,
Yeah.
I'm going through another pentagon. If I'm going through like this, if I go now through a triangle, I will go through another triangle. So ultimately, if I flatten the whole of this, it will flatten in the form, it will twist and flatten in the form of a disc, a circular disc, like she has it at the figure 14, 19, 15, 14, 19 of the region. If you see, she say the 15 great circle model. That is,
Yeah.
and you will have that wheel that you have there with the traces of a great circles. Do you see that? On the
Yeah.
15, the book, page 252, when she squashes everything into a circle, into a disc. 14, 15, 14, figure 14, 19.
1419. Oh yeah.
Yeah,
One
of the
left.
book.
Yeah,
Yeah.
119, I think, right?
Yes. So all is only, if you take this, you press it and then you rotate it. It's always compression and rotation. Compression, rotation. Or extension, rotation.
That's
Those are the two
tensegrity.
things. Yes. So it's a combination of the what Steve will call linear momentum with angular momentum. Always, it is to move, what you call in physics translation, and to rotate. If you do that, you will always be able to describe completely the surface or the inside of of any finite polyhedron.
That's right.
Yes, of any polyhedron anyway. Because when you say polyhedron is finite, the implication that it is finite. So you compress, you push like that, you twist it, you turn, and then you cut it. That's the way that we have created the three-dimensional space in which we live. Compression or extension, rotation left and right, and then splicing. Those are the three things that we do to divide and understand what is going on. Okay, I'm through.
Thank you, Manu. Lee, you have your hand up, but I would like to repeat my question because it has not been answered. So I will repeat my question, and then Lee, you can try to answer it for me, please.
Oh.
What does it mean that a vast number of molecules of gas interacting in great circles, etc.? What does that mean?
I'm not sure about that one myself, but I have just remembered a crystal, knowing that crystals are made with pressure, water, and they're a mineral. And what is so interesting is that I have a standing crystal about this tall, and at the top, which is to the point or the hexagon, underneath, just right down below the hexagon, is water flowing, and I can shake it and see the water moving. It's like the gas that Manu is talking about. I never thought about that. I just thought, okay, it's just part of how it was created. But it could be like considered a gas, except that it's a liquid instead of a gas. I don't know. Manu, do you have any idea?
Do we agree that a fold, an edge
Mm-hmm.
are the same thing? A fold and an edge is the same
Mm-hmm.
in a
Mm-hmm.
polyhedral structure.
Mm-hmm.
We also see
Yeah.
that all the triangles can share energy since they touch, everything touches everything. They can only share it along the fold, the edge, or vertex to vertex. Those are the two. It cannot fly, it cannot jump through a window.
Mm.
The impression of jumping through a window is actual fact is the radiation. Is many that goes out. But at the level of our seeing, energy is always going to flow from vertex to vertex through an edge or a direct contact of the vertex. So when it's vertex to vertex, there's no more fold because everything has been extended. It doesn't fold, you don't need. That takes too long. It is vertex to vertex, that is gas. I repeat this, if energy has to go from one point to other, and there are two events like that, that has one point to the other. If that energy has to go through the edge to edge like this, it's too long.
Mm-hmm.
The energy we prefer that have to be the other one to be the closest to the other in such a way that their ends, since they are finite events, the end touch like this, and that will serve as the shortest way to communicate. Energy flows, always flows to the line of least resistance. This is the least resistance here in gases. That's my best explanation. Maybe it's not going to take you anywhere, but it's the best that I can offer for that.
Thank you. How about gas? Where does that come from?
What about gas?
Yeah.
Where does it come from?
Why are we talking about gas here? A vast number of molecules of gas interacting in great circles.
Um,
What does that mean?
Mm-hmm. Where does it come from?
I think it's the confusion of language because she has repeated. If I were to say that, I would say a vast number of things interacting in great circle will create the minimum bond that I call gas. That's the way I will explain it.
That
But
that-
she repeated gas in a reading that is confusing because it gives the impression that she's going in circles. A vast number of molecules of gas interacting in is gas. That's what I understand from what has been written here. You could have said, in my opinion, better.
Okay, so the explanation is that Bucky's was not precise in his language.
Isn't it part of the entity or the molecule or the circles? It's just part of it.
Why do you
Like,
talk of molecule? We don't know molecule.
oh well, that's true.
Yeah.
Well, it
We
says
just know that
molecule
they are.
in the it says molecule in the
incorrectly.
citation from synergetics, a vast number of molecules of gas. So we know it's molecule.
We want to understand. We want to understand easy. I would just say the vast molecule of events, the vast number of events, because there are
events
events.
would make more sense to me.
Yes.
I mean that would
Yeah.
definitely
A vast number of events happening.
Okay, maybe I don't know. But it's unusual for Bucky to say molecule when he means events. But maybe that's
No,
what he means.
that's Amy. That's Amy. That's not that's
No,
not
no, no,
Bucky.
no. That's a direct. I checked it. It's a direct
Yeah.
citation from Synergetics.
Yeah, I
Okay.
think that there's
I have
what
the
happened.
Synergetics. I have the Synergetics book here. We can have a look at it if you want.
You know, it's interesting.
Let me share it.
There's
Synergetics.
a group that Richard attends, the Trim Tag group. It's I attended as well. They were putting, I think, every passage, and one person was going to work on putting every passage in Synergetics into AI to generate an image.
Okay.
But anyway, the
Can you
reason the
repeat
vast,
that again, Joe?
yeah, interacting circles sphere will produce. Oh, I can read it if people would like. I still can't see
No,
it
no,
though.
no. What you just said about generating an image, I did not get it.
That's another group where they're putting
Yeah.
each section of synergetics or sections maybe at certain points so that they then create an image of whatever is being described in a particular passage within synergetics.
Okay.
So,
Okay. And
but
Richard, have you drawn an image yet in your group of 70314?
I guess
Which I'm sorry, I didn't catch that.
I'm trying to understand the first sentence of 70314 in Synergetics, the one I'm sharing right now. A vast number of molecules of gas interacting in great circles inside a sphere, etc. I'm stuck on the molecules of gas interacting in great circles. I cannot figure out how that works. And Manu tried, and Lee tried to explain to me, but I still don't get it. And the best explanation we get is that it's maybe inaccurate use of language by Bucky, that instead of molecules of gas, he meant events or energetic events, maybe. And Joe came up with the idea that with a testimony that you're part of a group that studies synergetics and produces sketches or drawings or images based on each synergetics chapter. And I was wondering if you had one for this 703.40.
I don't think it's drawing images. I think what Joe is getting at is that one member from Austin, Texas, is with his ability to use apps and find them, digitizing the entire synergetics dictionary. And one of the challenges is to get all of the correct presentation of the definition cards, and to pick up little images and the right sort of punctuations. And he's having a lot of challenges in trying to find the right application that will do the best possible sort of digitizing. So I think that's what you were getting at, Joe.
what I was actually referring to, there was one person in particular at the end when it was during a session about, I don't know, it might have been right around last year, October. Maybe it's a little further than that, but regardless, that it was there was one member that was putting passages into AI and having them drawn. And whenever Lionel was actually bringing up reading a passage each day or something along those lines, that which he's doing, and one person was putting these images into AI to display what Bucky was saying. And I don't know. That's what I'm saying. That would help maybe explain part of this.
Yes. Yes,
part of
if
this.
somebody had a visual to explain it, I would have very much
Yeah,
appreciated
it would be a lot easier right now. So that was my whole point.
That's correct. I want to rebound on what Richard said about digitizing the synergetics dictionary. I've been thinking about that since July, actually, that's a bit more than half a year. So maybe, Richard, we want to get together and talk about it if you want.
Yes,
At
well,
some-
as I say,
at some
it's
moment.
Brett in Austin who is doing all this digitizing, working. He's digitizing all of Bucky's collection of writings and works.
Yeah.
Under, if you search Bucky verse,
Right.
you'll find the text of all the work that he's accomplished so far. And he keeps finding new books, either that are primary sort of authored books by Fuller or secondary sort of authored books about Fuller.
Okay. Okay. You said this person is looking for an app in order to be able to manage this information?
No, he is working with a number of apps, but he keeps trying to find the best one. So he's quite proficient in this whole area and knows it quite well. So he keeps testing different ways of doing it and keeps finding ways or better or improved ways of doing the digitizing.
When you say digitizing, that's scanning the work and put it into text that can be used.
Yes, yes, right.
Okay. Okay, thank you.
Yeah, it'd be worth for anyone that's interested is to say look up Bucky verse, all one word. But
yeah, he
it's
presented it. I believe he presented it 52 Living Ideas.
Oh, did he? Okay. Remember.
I'm fairly, if not, I've seen him present, and people have shared his web pages with me. Yeah, so he's
and if you search Bucky verse, you should be able to get a link into all of the collection that he's digitized so far.
Thank you.
Let's look it up, sure.
Okay, shared now is the synergetics text, the original text. Anybody wants to comment on that?
Yeah, the 12 and 30 hexagons and 80 triangles described by 240 great circle chords. I don't know. I feel like that has something to do with the video I'd seen. But I have to go back. The aggregate of all intergrade circlings resolve themselves typically into regular pattern pentagons and 20 triangles, or sometimes complexity into 12 pentagons, 30 shows. The only thing I could say about that is that it sounds like it's in a container. That's what I can almost get the feeling that the idea that it captures overlapping experiences within the circle. If that makes sense. I have to think about it.
Okay. Okay, sorry to stay so long on that, but I'm really stuck on this on this gas interacting in a great circle fashion. Let's move on. I've highlighted it on my book, and I'll see if I can return to it. Joe, are you okay to keep going?
Sure. Fuller's
Thank you.
hypothetical molecules are bouncing around so fast that the overall pattern of their activity seems instantaneous. But in reality, he reminds us there is no instant universe. Time is always a factor. Molecules collide and bounce back, equal angles created by the symmetry of their collisions create the illusion of full great circles in weaving. But their trajectories are really local loops. Now that's interesting to me. The triangles being a dynamically resilient, mutably intertransform one another, imposing an averaging of the random force vectors of the entire system, resulting in angular self interstabilizing as a pattern of omnispherical symmetry.
Okay. You said, after you read the last sentence of the previous paragraph, you said that's interesting for you. Would you like to share?
Sure. I mean, molecules, basically that their collisions create an illusion of full great circles interweaving, but their trajectory are really local loops. And I was like, I'm trying to think about what does he mean by local loop within that context. It seems like something that's collapsing, and that is a local experience of how, I don't know, but I have to think about it. That's interesting. Manu,
Is that the same as what we saw here? And earlier with bow ties that actually created.
Yeah.
And the previous one here, where we had the bow ties here creating the. We have the illusion that energy flows all around it, but in fact it flows in an interactive pattern. When the two great circles intersect, then the trajectory just takes a turn instead of keeping going. So they don't actually intersect.
I think something else. What he's talking about is that for me locally, is always action, reaction, resultant. That is the local loop. Action, reaction, resultant, and continuing. So you have like these triangles that are like that. You know, this is me. You know, just look at the experiment now. You are Joe. No. Manu speaks. Action. Rebound somewhere. Reaction. And then come back to you in the form of resultant. That is what the state at an interval following at the future. So it's always a local loop of action, reaction, resultant. Action, reaction, resultant. So when I create action, reaction, resultant, my resultant becomes an action to somewhere. And the two are always interacting. Imagine like if you take a necklace, you have the circle of necklace that come together always like that. You have one node, another, you call it node, like that, and then it continues. That's the illusion that we have. But it is, for our understanding, it's always local loops.
Yes.
Because all we measure is action, reaction, resultant. That is a pattern that we always measure in everything. Action, reaction, resultant. You have a cause, that is a sine. You have reaction, that is cosine. And then you have the tangent of it, that is the resultant. So the tangent, that is, I always associate the tangent with like tangent in the language that we use. When you say somebody is taking a tangent, you mean he's taking a turn from where you intend to go. When I say, if I'm speaking with you and I make the remark, but Joe, you are taking a tangent here, it means to me, you're not going in straight line. You are taking a curve.
Right. Right.
Okay. And you see the origination of what you call angle is a deviation.
Right.
Action,
That makes sense.
reaction,
Action.
and there's always a deviation.
That's right. That's right.
If not, is a pushover. Push.
Which means it's a dual.
That means if you say pushover, it means that there's no movement because everything being stable at the greater level, if you push, it's just action reaction that is right opposite to it at 90-degree angle. Impact is zero. It's like that.
Okay.
I see nothing. I just see a point in that projection. But if there were angle, I will see a cosine member of it. And there will be a reaction that will be expanded. That is the hypotenuse of that triangle. I'm through. I hope it has advanced us. Otherwise,
No,
I apologize
I mean,
for taking the detour.
it is one of those things that I have to revisit, but I do think that the way you explain that gives me a lot better of a chance of understanding it. I mean, thinking about it as local is really the key. And finding our blind spot.
Our reality is local. Let's just put it clear. Everything else is speculation. What we call reality is what we see on our screen. The screen of projection of our senses. That's our reality. And is always and will always be local. Everything else is relational. That is, we imagine it. We anticipatorily imagine it.
That makes sense.
Okay. Shall we keep going?
Yeah, I think we should give it a shot.
I need to share. Share.
We're page 256.
Or 253.
It's hard to tell. Hang on. There it is, the loops. I got down to where did I get down to? The
We're
7th.
here.
Yeah.
Yeah.
Exactly.
What page is that? 253, you say?
I think it's
253.
different.
253.
Page is 253. Thank you.
Yeah, I think it's different. Well, I don't know.
That's where we are.
Yeah.
Okay, yes, gas molecules. That's one. Yeah.
Is that 253 in the book as well?
Yes.
Okay. To Fuller, the ability to fold individual paper circles and automatically generate an entire symmetrical pattern gives great circle models important physical relevance. They demonstrate his statement that no two lines can go through the same point at the same time and illustrate the concept of interference patterns. The model, says Fuller, is constant with physical behavior. Although physical systems are always imperfect, the result of a vast number of interactions is approximate symmetry. With enough data or time, all possible paths can be tried, and the properties of space come into play. what does a maximally symmetrical distribution on a spherical surface look like? The aggregate of all the integrate circlings. This is where I think it's that constantly overlapping that we're actually always interacting with one another, and you have inside of the universe and outside. But anyway, that spherical distribution, spherical surface look like? The aggregate of all the integrate circlings resolve themselves typically into a regular pattern of 12 pentagons and 20 triangles, or sometimes more complexly into 12 pentagons, 30 hexagons, and 80 triangles, described by 240 great circle chords. The pattern is always icosahedral, some version of the maximally symmetrical shell, referred to chapter 11 for a comparison of space filling versus shell symmetries. Icosahedral symmetry fits the most great matter, the most great circles on a closed loop. One notable characteristic of this pattern, no matter how high the frequency of subdivision, is the presence of exactly 12 pentagons evenly distributed around the system, one at the location of 5 valiant icosahedral vertex. The 12 pentagons and only 12 will persist as constraints. Also, the number of triangles will occur in multiples of 20. I think, shouldn't we scroll? Okay.
Do you understand what he said here? In summary,
In the summary, no.
it's IBM.
Oh, well, that makes sense, actually.
Yeah, that's it. So if you go into high and high division, the first remark that I wanted to say, do you know what he called the law of large numbers in statistics?
What did he call it? Large?
When you have large numbers, it always go to a normal.
Right.
Okay.
So
Now,
LCD? Yeah.
yeah, but that was the digression. What is describing here is the IVM. Is that you always have the repeat of a cube octahedron. We read this at the 12 vector is a vector equilibrium. And you always have, it's like a catenation of those things. So when you look at any direction, it's always the same. It looks the same.
Interesting. That made
And
it a
you
little
understand the 12 and 20? 12 vertices and 20 faces of the icosahedron.
right.
And in anticipation of what we're going to read, that's why they say the icosahedron is the shunting of universe. It's instantly, it's not through something that you see. It looks like everything just go into stability in the icosahedral form. We're going to see that further down. It's called the icosahedral shunting of universe.
Ah, okay. Yeah. Yeah.
You know the shunt in electricity? That's a
Yeah.
bypass. Yes. Okay. So to me, you can go into this complicated language, or you can jump into what makes sense in light of what we
Yeah.
are reading.
I agree with you on that.
And that's what he's saying. That's what I'm understanding. I might be wrong. I'm true.
Next page. constant number of pentagons together with 12 spheres around 1 and 12 degrees of freedom suggests fundamental 12ness inherent in space. We shall return to this pattern in the next chapter, looking at geodesic structures. Fuller uses models bouncing around in a spherical system as a model because molecules are energy events occurring in large enough numbers to describe the symmetrical patterns developed as polyhedral abstractions. In conclusion, energetic behavior is subject to symmetrical constraints, and in order to adhere to logic or theory, probability calls for very large numbers. My eyes are really
that illustrates a little bit. That helps the comprehension of
yeah.
the gases. Thank you for reading that. I'm going to annotate it, maybe. I like this. There we go. It's 36. Is that a good place to stop, or shall we keep going?
I mean, I mean, how many people we got? Let me see. How long's the next section?
So 6 of us. That gives us each 4 minutes.
Yeah, I think that's fine.
So, Manu.
Hold on. Hold on. I was suggesting that we just go. Did we go to the end of to where we started with great circular railroad trucks, tracks of energy?
We read into that, yes?
No.
Okay, so that I'm fine. Yes.
That's where we stopped.
Okay. Yeah, we're fine. I'm fine.
I think that's a good place to stop, and it's about time.
I agree.
To do
I agree.
something. So,
especially since we're losing an hour's sleep tonight.
Yeah.
is that true?
Yes.
Yeah.
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 Also, you've all changed time to daylight to summertime.
Yeah, pretty much.
Okay.
No, we don't lose it. We gain it.
We gain it
Well,
if
that's
it's the end of the day,
eternal
but
discussion. Nobody ever
sleep.
agrees on that.
We lose sleep though. We gain the day. We gain daylight, lose sleep.
Well, you don't go to bed at that time, the new time.
That's true.
Yeah.
All right. Manu, how are you feeling today, and what is your takeaway?
I feel good, and I think that this was a very good session. I think it will help us to always like try to go back to principles, and I think it simplifies a lot the understanding of verbiage of description. So I'm very happy of the progress that we had today, and I think that we saw the practical side of it. Notably, that there's always, localized events that interact to make the great things, and it connotates a lot with Fuller's description of what he calls universe. And I'm also happy that somewhat we came back to our IVM, that we look way back at the beginning. In that somewhat the natural interaction of many things tends to a certain equilibrium that is icosahedral, and that tends to repeat all over.
Right.
And when you say icosahedral here, it means icosahedral expanded. So it means the icosahedron and the dodecahedron together, because that's what he's describing here. That's why it talks about the 12 vertices and the 20 faces, because that is the characteristic of a duality of the two that interchange.
Yeah.
Depending on how you look at it. The 12.
Yeah, and I think that if that's an example
This is the 12 here. If you take the center of this pentagon, there are 12 of them in this schematic. And it's constant. And then you have the faces that we see. You have 20 faces, 20 triangle, icosahedron, whatever. She called it some kind of expanded icosahedron form. And that is the shunt of universe. That is the most expanded, the gaseous state that comes in the form of the icosahedron. The icosahedron expanded like this is the only one that is consistent with the notion of the most expanded having triangles that, remember, we see only triangle. The pixels are triangles. What we call pixel is a triangle, is a loop, is the surface inside a triangle.
Interesting. Oh,
Yes.
yeah, that makes sense.
Yes. So what we see, he says that that is the most consistent between the vertex to vertex description of what he call gases and the geometrical description that we have here. That's why it goes back and forth between the two, and it uses those words. So that's my biggest takeaway here, is the practicality of it by going back to principles and try to tie them to what we see in general and the model that we can construct.
Yeah,
That's
I
it.
agree with that.
Okay. So I'm grateful for that. Next is Lee. The only female on this call. Come on.
Alvin? Yes.
Yes.
Thank you, Manu. I'm feeling really in tune tonight with what has been explained. I really do understand all that is happening. And I am excited to start the Great Circle Railroad tracks of energy next week because I love trains. Just to clarify why, I would be interested in the Great Circle Railroad tracks of energy to find out what's all involved in that. Joe, how are you feeling? And what is your takeaway?
I'm feeling pretty good. Again, I think that again, what I mentioned on the outside is the idea of the Philosopher's Stone, and how that actually, if I think about it in those terms, I'm able to grasp it a little bit more quickly. And by seeing those, the way a star actually comes together within that diagram, was very helpful for me. So when I'm engaged in calls like this in particular, is I always think about how to extract, which sounds a little bit I don't know, unkind, and uh you know basically the idea of extracting and kind of thinking through. I lost my train. I'm sorry about that.
You look tired, Joe.
I'm a little tired, but I also got a little bit distracted there a moment ago. But yeah, in any case, having something to look through an orientation, you're able to see things a lot more clearly. And I saw the patterns, and the patterns are followed by numbers, and then you could start to put things together. And so I'm excited about that. I'll pass it along to, I don't know, Richard?
Yeah, sorry about that. Just my own distractions here. Had a phone ringing in another room, and I had to go see if I could catch it. Yeah, it's I guess I'm still connected to, as you say, trying to take the basic tetrahedron and taking it out of that three-dimensional mode, laying it down into two-dimensionality, and then back up again, and then finding the practical applications, which I've worked out in relation to my discipline in terms of having a conceptual model that includes the systemic and the systematic. And the other that, and I'm pretty sure I got from Steve some time ago, I've been using the notion of precession, and in this particular model, and then he spoke about the 6 motions that involve the out of the vector equilibrium that involve torque and orbiting and expansion and contraction and in and out. And I tried to apply all of those to the conceptual model that I had constructed out of the tetrahedron, and also just using the principle of precession. And I found all 6 applied in terms of how you can torque something in order to tighten up or focus in or unwind and loosen up, or how you could have 2 not intersecting, but parallel lines that are connected with a relationship that you can come in close and again be really in touch with the other side, or you can separate out and in a sense back away and be distant, or you can take somebody's pathway if you want, and it can overlap the adjacent pathway in such a way that it is a model of manipulation. So it shows how somebody can try and take over somebody else's agency or their pathway and control it. And that works both ways. In a so-called clinical type relationship, you can have the client try and take over and control the helper, or you have the reverse where the helper tries to take over the line and then pull or push it in the direction that they prefer, as opposed to what the patient or the client prefers. So I continue to work with that, and I'm still getting to the place where I can really feel the applications out of things like the icosahedron. And of course, the best one for me at the moment is the Dymaxion map, and show how it can lay down into a configuration of the earth and water relationship. So I'm taking more of that out and getting ready to be able to expand my application of the modeling into practical ways of applying it. So thank you. And I missed whether I'm the last one. Is it back up to Fred?
Try Steve and see if Steve can possibly. But I'm guessing it would go to Fred. You're muted, Fred.
Thank you, Richard. Steve is not there, I believe. He had to go on a family event, so he shared hosting with me today, so he's not there. That was a good call. My takeaway is that when you don't understand the sentence in Bucky's work, just keep reading. It's explained later on. So I'm glad we got to the point where the molecules bouncing are energy events occurring in large numbers. That's good, and that ties up very well with Manu's explanation. So I'm very grateful for that, for the effort that you guys made to helped me get over this bump in the road. I very much appreciate that. Thank you, Lee, also for your contribution. That was wonderful. And Joe also for the reading. I appreciate that. That was not an easy chapter to read. And
No, it wasn't. No, it
I'm
wasn't.
very grateful you took it on and you did a good job of
Thank
it.
you.
And thanks, Richard, for sharing the work that's being done on Synergetics Dictionary. I think that's very important because Synergetics Dictionary is a wonderful work that should be used very often as a reference when we use words or when we see words from Bucky's work. It's very rich, but it's very clunky to use either on paper or on PDF print, on computer, or even via the original digitization of it. That's it's online. You can search for it, but it's really clunky to use and difficult. So if somebody gets to the point where we can use it as a wiki, where you just get a definition and links, linking the different definition and concept and all these things, that would be really, really helpful and useful. This is the kind of work I would be happy to contribute to. So if there's an entry to that to that task, I'd be grateful to answer to it. And there we go. So thank
Oh,
you.
wow.
Thank you all
Well,
for showing up. And that was a good call. And see
Thank
you all
you.
see you all Wednesday or next weekend.
Wednesday and weekend. Bye-bye,
Yes,
everyone.
almost.
Good luck,
All right.
everybody.